ये पीडीएफ है ना
Good afternoon, everybody.
Good
Hello.
afternoon, sir.
Yeah, maybe those who had issues with the voice, can you just check whether it is working today? Last time, I think Akhtar had a problem. And I think Shreya had a problem. Who else? I think Saurabh also had some problems. Can you verify that you're okay now today?
Yes, sir.
Yes, sir.
Very good. Very good. Let's make it more participative and interactive than last time, but let's also do it quickly because at the rate we went yesterday, I couldn't even cover 1/3 of what I planned to cover yesterday. Okay. So we were, just to do a recap, yes, last class we were at, we had from the previous session, we had identified the evolution of bridges. From the evolution, we understood the bridge systems. We identified the 5 major components of it, and we are now dealing with the first of the components, which is the superstructure. And in the superstructure, we had seen a gradual progression from slab type till truss type. Okay, so let's take off from where there, and let's move on. I just wanted to know how to, on my screen, how do I see you as well as my presentation? Can anybody help who is familiar with Teams? Because if I see my screen, I can either see my presentation, I can't see you all, or I can see you all and I can't see the presentation. Is there any way I can see both? Okay, I'll leave it for today. I'll find out from the IT people. I think Milind, your camera is switched off.
सर इसमें थोड़ा लैपटॉप में इशू है, इसी के लिए थोड़ा लेट भी हो गया मेरे को ज्वाइन होने में।
ठीक है,
बस मीटिंग ही आज हो पाएगा लग रहा है, इसमें मतलब कैमरा ऑन नहीं हो पाया।
नहीं, it's a dark screen. It looked like your top में एक switch होगा लैपटॉप के ऊपर. You may, that switch might be off right next to the camera. There is a horizontal switch. If you can adjust it, your camera might get on. Okay, right. So we took off from the evolution to the components, bridge components, and superstructure. We were looking at it, and we ended up at truss. So let's move forward from that point onwards. All right. So let's let me share my screen. Yeah. Right. You're able to see my screen?
Yes, sir.
Right. So we were at the level where we were discussing. I gave you one question to think about. I want you to think about it and get me an answer maybe by next week as to what's the advantages and disadvantage of how truss and flat truss, one over other, right? We saw one structural efficiency, we discussed a lot. Then why was how truss discovered or invented? Not discovered is wrong, invented. Okay. Now we were discussing on how the trusses can be arranged, underslung versus through bridge, and we can also have what is called as a what happened? Semi-through truss. Okay. What exactly is semi-through truss type of arrangement? Right. You see, this is an example. This is it is called the fourth bridge, but it is not the fourth FORURTH. It is FORTH, fourth bridge, and it's a very old railway bridge, as you can see. And what kind of bridge is this? It's a truss, definitely, but in addition to being truss, it's another type. What is it? Can anybody identify?
Cantilever with the
With a
supported span arrangement.
that word here in the center is called the suspended span. So basically, it's a cantilever bridge assembled from the pier outward, and finally a bridging suspended span is lowered there to cover the gap. So this is a cantilever bridge, and in which the traffic is going through the truss. So this is what is called as a semi-through. For major portion of it, part of the truss is below and the part of the truss is above. And of course, the suspended span is a classical through truss. Now, do you know of an example like this in India? Anybody? Hello? Can you hear me? Hello? Am I audible?
Yes, sir, we can hear.
Yes, sir.
So
Yes, sir,
I'm
you are
asking,
audible.
are you aware of an example similar to this in India?
No, sir.
Huh? Who was that? Who said no?
Shruti.
Huh? There you are. I was expecting an answer, especially from the Calcutta office guys. You have a very similar concept. A cantilever bridge with a suspended span in the very famous Howrah Bridge. Howrah Bridge is exactly like this in the conceptual stage. Okay. So semi-through type is popular for what reason? The reason for that is you're utilizing the depth below the rail level also for structural purposes, especially for very long span. Okay, it's a bridge built over 100 years ago. And the concept of this is very simple. You have this cantilever and you can support a load of a man. What does it require actually? It requires a anchor, as you can see at the side. Can you tell me what decides the anchor? What the size, strength, etc. of the anchor is decided by what? This is your suspended span. These are your two balanced cantilevers. You don't think these are structurally equivalent? And you have a counterweight put here. What decides the amount of counterweight or the anchor system, if you want to put it that way? You not always have counterweight. Yes?
Weight of the suspended span.
Okay, so the weight of this man, okay, that's the load carrying. Yes, that's one part. Anything else? Anything else? Think.
The uplift in the spans,
Huh?
the uplift in the side spans.
That's what I'm saying. How do you decide on what all controls the amount of this? Let us say, is this thing stable if these anchors or the counterweight are removed?
No, sir.
It is not stable. So that's the question. The question is, in order to bring in the stability, you put in this counterweight. I asked what determines the magnitude of this counterweight or anchor. I use two words. You can either have counterweight or you can have an anchor. Somebody answered the weight on the span. Yes, that's one part. What else? Is that all? To an extent, it also depends upon the span. To an extent. That is why if you look at the olden days, they would try to minimize the suspended span. They would try to, and if you want to see an example of it, if you take this bridge, it's much smaller than that. But if this becomes too small, I can show you a few examples where this has been reduced to 5 meters and 4 meters. And there we have a serious vibrational issue problem. So it cannot be too small, but it also depends upon that. And that's where this counterweight magnitude is decided upon. As a basically, the way this operates is you have a tension. You have to understand all of it in the form of a tension and compression. You have the tension being provided by the hands of the man, the compression provided by the rods that and the suspended span. You have a beam bending behavior. You have a tension compression at the top and tension at the bottom. So this is the simplification of the same thing in a very beautiful and elegantly put up sketch that is two people can carry a full man's weight. Okay. Next, we move on to the arch bridges. Now, arch bridges classically, there are two types. You have a conventional arch, and in the conventional arch, in an arch bridge, how does the force transfer take place? How does the force transfer take place? That is the end consequence. But in the arch itself, the force transfer takes place by what?
Axial force.
Axial compression, significantly axial compression. If it was UDL, we could have, if you were always guaranteed of a uniformly distributed load, we could always come up with an arch geometry which has only axial load. But practically, we cannot guarantee a UDL because we are talking about road bridges or even railway bridges, because positioning of the live load may not be uniform. Partially loaded arches will always have a problem. So we end up having a mixture of axial load and bending, but an arch behavior is something in which significantly it is a axial load. So from the geometry, the axial load transfers here and transfers here. So what can you do about this portion? What can you say about the qualities of this seating that you need to make arch? They can be in any type of strata. Yes? No? Silence is disheartening. Okay. I will do a small construct here if it helps you understand the this is the orientation of the force, correct? At both ends, similar one on the other side. Yes, no?
Yes.
Yes, sir.
Yes? Yes or no?
Yes, sir.
Yes, sir.
So if this arch has to work, what can you say about the strata here? What should be the nature of the strata here? Okay, I think that is also possibly insufficient. Then I will make it a little more simpler. You can resolve this into components if you like it. So you have a Vertical component, you have a horizontal component. If I draw it like that, it will be easy for you to say, yes, the vertical component will be taken, will be directly attempting to go to the ground. How is the horizontal component to be taken? That's a question, correct? Yes or
Yes,
no?
sir. Yes.
So what does it say about the requirement of this foundation strata for a classical arch bridge? Right. So it needs to be very strong.
Anchored into the
What do you mean by anchored? Let us say that I have a clay here and I put an anchoring into the soil. Is that good enough?
no, sir.
So anchor is not the answer. So what is the answer? The answer must be in the shear strength of the soil itself. It must be very strong to take care of this horizontal force. Vertical force, we know, because even your footing is designed for vertical load, correct? Why is it that footing is possible in all kinds of soil, but arch is not possible in all kinds of soil? That's all. And arch? Shear strength also. So now question, therefore, where do you get the shear strength in soil best? Where do you get the best shear strength in soil? In rocks. Stiff clay, no. Unlikely for you to get lateral resistance. Shear strength you will not get. Not much. Okay, compressibility might be reduced. But shear strength may not be much. So therefore you need something like a rock, which means what? Arch can be built only in pure arch. Can be built only in what kind of terrain?
Rocky terrain.
Only in the rocky terrain. Therefore, you see the famous Chenab Bridge that we recently completed is a classical arch. Yes or no? Have you seen the photographs of it? Yes, no.
Yes, sir.
You have?
Yes.
Or you're not curious?
More curious.
No, more curious. Then you should have said, yes, I have seen it.
Yeah.
Just hold on. Let me see if I can locate it for you quickly. I had it somewhere. Just hold on. Just let me. Yes, I have. But I have to share. That's the problem. Okay. Stop sharing, share. You're able to see this?
Yes, sir.
Yes, sir.
So don't worry about the first one. First one is only an artist conceptualization. And the other photographs are from this bridge during its construction at various stages. So this is when the arch was starting. And as you can see from this picture, it is on very hard rock on this side and an equally hard rock on this side. And that is how this arch has been built. It's about 450-meter spans. And as you can see from this photograph, clouds are below the bridge. It's at that height above the Chenab River. This is the Chenab River, which normally flows. So you can see stay cable construction during construction, and then you're seeing the building of the spandrel arch. You are also seeing another interest. Sometimes I will talk to you about different methods of construction if I get a chance outside this course. Then you can see that there's an incremental launching of the deck is going on from both sides. And this one came and this one came and they got joined in the middle. And they're only pushed. Assembly is all done on this side. And after they assemble a portion, they push it. I mean, if we want me to, the assembly is done behind here, and then this is pushed. Assembly is done, that's behind, it's pushed, and there's a launching nose. It gradually comes and sits, and finally it will come and join in the middle, this side, and that's where it will stop. Then they will connect it up together, and you'll have a continuous bridge deck on top. So they have different methods of construction. Arch construction, you can see incremental launching construction. We'll see this on another day. Okay, I only wanted to tell you that arch construction, arch requires a strong strata, and an example of this is there, right? So what happens if we don't have a strong founding strata? So do we stop building? Do we stop using bridges? We don't. If you release the horizontal force, the arch will fail and collapse. You cannot release the horizontal force. The whole arch works with the ability to provide this resistance to this lateral load. So that is why we modify it and we call it to a tied arch bridge. This is done so that in the end, the bearing location, you have only vertical loads. The horizontal loads are mutually balanced with each other. So this type of tied arch, one classic example of this tied arch, which have you seen anywhere? You haven't. I have to take you all on a travel of India. Only to see the bridge structures.
So bowstring जो bridge रहता है वो ऐसे ही बनता है ना?
Bowstring girder is exactly an example of this tied arch bridge. Have you seen bowstring girder bridges? How many of you have seen it? Anyone, anywhere? No, if you tell me the name like that in your local state, I wouldn't have. Yes, I'm very sure it is there. Bowstring girders are, a number of them are built in Bihar. Many of the ROB spans are like that, and I am aware of quite a few that are built in Maharashtra. Then mostly railways have adopted it as one of the standard designs. So if when you do the tied arch, basically what you've done is this lateral load from this side is balanced by the lateral load from that side in the form of a tie. Do you know the oldest tied arch bridge in the country? One of the oldest, I shouldn't say the oldest. Anybody knows? One of the oldest tied arch bridges? In Andhra Pradesh. When was it built? Any idea? Good. Now I'll show you one of the oldest. I can't definitely say that this is the oldest. Can you see my screen now?
Yes, sir.
Yes. How many of you are able to recognize this bridge?
Napier Bridge.
Absolutely right. Napier Bridge. And do you know when it was built? Approximately. No idea? This was bridge. This is in two phases out of which I am not able to identify which is the older one because they have been recently painted together. But the older one of them was first built in 1946. This is on the mouth of a river, which is just on the, I don't know which side, I think on the right hand side, it goes to the sea in our city of Chennai. There's a bridge 1946. It's a series of tide arches, simply supported tide arches. They're not continuous. And another interesting thing for it is the bottom tie. All these is called RCC, but the bottom tie alone is pre-stressed concrete. So it's a pre-stressed concrete also example. You can say it's one of the earliest examples of pre-stressed concrete in our country, 1940. So you're talking about almost 70, 80 years. It's coming to a pass. All right. So don't think that all the bowstring girders are new ones. They are very quite old ones. Quite old ones exist. All right. So tide arch. So the question to understand from this, tide arch is done when you are unable to. You still want long span. You still want to use the material efficiently, especially concrete. In which case, it's very strong in what we call it compression, but the tension has to be handled somehow. So the tension is handled by means of a tie. Again, the question is the tie as a reinforced concrete will become very expensive, very heavy. So therefore, you end up doing something like a pre-stressed concrete if it is possible. Quite often, a lot of examples you can see in steel bowstring girders. I'll show you some other day. A lot of maybe I do have some example of steel bowstring girder to show you. No, I don't think I have a good example of a bowstring. I had it somewhere, doesn't matter. I'll show you some other time bowstring girders. And essentially I try to show you a lot of examples which are done in India, preferably by our company, so that we have an idea that we have a whole string of examples of these projects done in-house. Okay, so then the arch arrangement, there are two types. You have the underslung arch, wherein the arch is below the deck. What we saw Chenab Bridge is a good example of this underslung bridge, where you can see the arch is primarily taking the load, and then there's a through arch type. And the through arch type, a very good example is the Sydney Bridge. I don't know how many of you have seen a bridge in Sydney which has got an arch which is partly below and partly above. There are a number of examples, but that's the most iconic to say the thing, and wherein the road or the traffic level is in between the two. Okay, so arch bridges we tend to use when we need force transfer primarily by compression. So we started off with a pure bending member. Then we went to slab, which is also slab box girder, is a bending, torsions are handled. Then we moved to truss, which is basically transferring all the forces to a combination of tension and compression. Then we moved to an arch, which is primarily compression. And from there onwards, we can move to another type of bridge, which is an integral bridge. It's very difficult to ask you whether you have seen examples of it. It is there are quite a few of them getting built in our country. Some of them being actually have been done from our offices, and some by many other people, many other consultants in the country. So what do you see an advantage? Do you see any advantage in integral bridge? Or let's understand, what do you understand by this integral bridge? You have seen the conceptual sketch on your screen. What exactly do you see as an advantage in integral bridges? Any? None? Yes? Please take a call. absence of joints. What joints? See that as I told you at the beginning of the class, we should be, as we go along, we should also learn how to do our expressions precisely. So what joint are you talking about? This is not a joint? That be precise. Should I say absent? In this example, it is not absent, but yes, you are right. There are expansion joints are eliminated. What else is eliminated? Or I should use the word minimized if you want to put it that way. What else is?
Bearings.
Bearings are also minimized. In this example, there is a bearing. In this example, there is a bearing, but there are examples in which this is also integral with an abutment. There are examples of that also. So the question is, why do we do it? Now, what's the advantage of it? Maintenance of what? So bearing is a maintenance intensive component according to you. Fine. Okay. That is reduced a little bit. Then what else? Have you traveled on Indian roads? What do you mean by riding quality? Be precise. Why? Should there be? First question, we are all bridge engineers. My question to you, should there be? But if they are, why? Why are they? If they are there, why are they there? Oh, you think naturally it will come in or some other reason? Why are there level differences in expansion joints? Please. Why are there level differences in expansion joints? Okay, let's go the other way around. Should there be level differences? Is that how you make your drawings? When you make how many of you have prepared any general arrangement drawing for a bridge? How many of you have prepared?
I'll tell you how much it will cost.
How many of you prepared general arrangement drawing for any bridge in your career so far?
Sir.
You have prepared.
Yeah.
So have you shown level differences at the joints?
No.
But do you agree that there are level differences?
Definitely will be.
Definitely they are there or they are not there. Or sometimes they are there, sometimes they are not there. Yes, please. Anybody else? Today the class is very silent. There's no fun today.
Just because the slab looked like somewhat cantilever after that bearing portion in that case of expansion joint. While traveling, it will
even the girder will deflect. Are you telling me there is any structure that does not deflect under load?
No, but it is not going to happen in uniform manner. So,
are you sure? That's the main reason.
No, not like that.
2 seconds you withdraw your view. You should be firm.
But
okay.
It may be one reason.
One reason. Okay. I'll grant you that it's a small reason. How much do you think the cantilever deflects under the wheels of a vehicle? How much do you think the cantilever is typically from the bearing to the expansion joint, if it is there? How much do you think it will be?
It may be 1 meter or what the center of the bearing to the
center of the bearing to the expansion joint generally is of what order?
Is 800 to 1.2 maximum, 1.2
maximum
meters.
1.2. Out of that 1.2, you also have the projection of the web a little bit.
Yes, sir.
And then you leave maybe about 500, 600 mm.
Yeah.
Is all there. 500, 600 mm cantilever will deflect. Definitely. I don't say no, it will deflect, but will it deflect enough for you to feel the bump? So why do you see the bumps? That's a question. It comes out of the fact that we don't install our expansion joint correctly. We don't do the profile control of our bridge correctly. Next time you travel along the bridge or you see a bridge under construction, you should stop looking at it as a tourist attraction. You should look at it from the eyes of a bridge or infrastructure engineer. What they are doing right, what they are not doing right. You have to. Okay, Praful, you can take a break today, but you can catch up on it through the recordings later on. All right. Okay, so the thing is, you have a small cantilever. They will deflect, no doubt about it, but that's too small. Most of the time, it's because the level and the profile is not controlled properly. Some other day we will see how the expansion joints. One day we have so many topics to come because these are all small detail things which you will not learn anywhere from the textbook unless you see it yourself being done sometimes, and then you will start crying. Why are we civil engineers and structural engineers doing this way? Okay, and then you will feel very sad that our practice is reduced to this level of carelessness. Okay, so it's primary. So you're right in saying that it reduces the number of expansion joints, the integral bridges. Okay, they do reduce it, and the main reason for that is poor geometry control during construction, and therefore you're eliminating one problem. But geometry control could have been done in many different ways. Expansion joint is not the only one, but that's a good idea. There will be other costs that will come through the integral bridge. We'll come to that a little later when we are studying movements and things like that. All right. So generally it's done for continuous spans, and it's a good example of a integral bridge. A very long span, and you have a connection. Column itself is made raked or inclined so that you have basically this longer span from here to here is reduced partly by this. So therefore the structural depth here, you have continuity here. It also induces huge tension, so you need a pre-stress here. All that is, but it's a very beautiful example of an integral bridge. No bearings there and fairly long length. It may be, in my estimate, this will be almost 400, 500 meters when you see from expansion joint at other end to the expansion joint at that end. This end to this end, maybe easily more than 600 meters spacing of expansion. No expansion joint in between. Completely integral between the deck. No bearings either. Right. Now we move on to. Now we go to structures which predominantly transfer forces through tension. So we first saw bending, then from bending we graduated torsion, then we graduated to a combination of tension and bending, then we saw some example of pure compression. Now we are going to see examples of pure tension. Practically, I'm not saying always, there'll always be bending. We cannot, as long as we have a deck slab, we'll always have bending. So in this cable stayed bridge, if I were to ask you, typically these are called pylons. These are called pylons. Typically, what will be the distance from pylon to pylon? Are you aware of any cable stayed bridge built in India? Yeah? No?
It is usually between 300 meter to 400.
300. Who is that? Just as I told you, since our cameras are off and I can't see, you can just tell who you are and then tell.
Sir, Akhtar.
Akhtar. You say 300 to 400 meters. Akhtar says 300 to 400 meters. Anybody else? Up to a kilometer. Okay. Who is that? Chukalyan, up to a kilometer. Okay. Currently, do you know what is the longest span of such a bridge in India? No idea? No, I'm talking in India. First, we'll come to India. I know once you say a kilometer, I know you're generally aware of where it is located. But in India, do you know what's the longest bridge
I
with
think
pylon,
it is
longest
Sudarshan
pylon to
Setu,
pylon
sir.
distance? That has been built yet.
Sudarshan Setu, sir.
Huh?
I think Sudarshan Setu, sir.
Sudarshan Setu, where is it located? Google search. Good. It's located in a place called Okha, or they call it the Bet Dwaraka. There it is a 500 meter span pylon. That is the longest. It's longer than the second Hooghly Bridge, which has got 440 meters center to center. But that Sudarshan Setu will remain longest for maybe another 3 or 4 years. We have one bridge being built across Beas as a part of Amritsar Katra Expressway. Delhi Amritsar Katra Expressway across Beas is being built, which has got a 750 meters or 700 meter span pylon. All the others, what Akhtar said, typically in India, 300 to 400 is there, but there are not too many examples. From 350, we have 500, now 500 to 750. Otherwise, typically, they are from 150 to 350 in India, typically. But what Chukalyan mentioned, the longest one is Russky Bridge in Russia, which is about 1014 or something like that meter span, pylon to pylon. Now, in this cable stayed bridge, we'll come back to some other day on understanding why they are called cable stay and what's it different from other types of bridges which look similar, like the second Vivekananda Setu, which is another term you might have heard called extra dosed bridges. What's the difference? We'll go through that some other day. But primary load carrying member in this type of structure are these cables. These are called the stay cables, and they provide the stiffness to the deck through their inclination. And the steeper the inclination, what do you mean by steeper? I mean this angle, higher this angle, more stiff the cable is, and therefore in cable stayed bridge, these pylons are very tall, and there are some optimized geometries for that. We will see that later. So once this is a type of a bridge in which the main span pylon to pylon today in the world is about a kilometer. They may do bigger than this sometime in future. Then you have options. You can do this way or you can do this way. Which one do you think is better? Say the top one is called option A and the bottom one is called option B. Which one is better?
Second option, sir.
Why? That's what you have seen. You have not seen that. Why do you say this is better? See, remember one thing. In this class, if you choose an answer, I will always come back to you and ask you why.
Inclination of the cables.
What's the difference between them?
The slope is more in option 2.
Yeah, but I could have made this taller. I could have made this taller also.
Okay.
That option always is there, no? What's the difference between the two? The difference between the two is then overlapping of cables in some zone. So the question I asked you was, which is better?
Option 2.
Why?
Any losses of the cable due to that overlapping?
Remember, in all cable stayed bridge, the design condition is the bridge should be still safe for loss of one cable. It's a condition throughout the world. Even if one cable snaps for whatever reason itself, the bridge should not fall down. That's a condition. So loss of cable is not accidentally one cable can go. Accidentally many cables cannot go. It has to be deliberate action. And I know you cannot prevent failure of a bridge due to deliberate action. So loss of cable, when you use the word, I'm assuming that either through a natural phenomena or an accident. Am I correct in that understanding, or you have different understanding of loss of cable?
It's not loss of cable. The loss is whatever that due to the overlapping.
What is there in the overlapping loss? Why? I can always detail. Then you have to see the pay. Okay, there's another arrangement wherein these cables, when they are arranged at pylon, they have got a multiple different types of arrangement. One of the oldest form was what is called as a crossing cable, which were like this. Which, if I were to show it to you again, as I told you, I can't see you and I have to come out of it. So they were crossing cable. That is how they were anchored in pylons, some of the oldest cable stayed bridges. We may not do it now, but the earliest one's cable. So whatever you say crossing, they're crossing in pylon, they can cross open. What's the problem? Why all of you, okay, let me ask one question. All of you think that the second option is better. I'm talking structurally. Second option is better. Yeah, I want you to all think about it and give an answer. What is the type of this bridge? What is the type of this bridge called? Name that we have given here. It is written on the slide. Cable straight bridge. Okay. And I said, how does it offer the strength? By becoming stiffer due to its inclination. So if I were to ask you, what about this bridge versus this bridge? Let us say they are the same span. I have adjusted the pylon to get this arrangement in one place, and I have adjusted the pylon height to get this arrangement. Tell me, between these two, this deck versus this deck, which is stiffer?
Option 2.
Huh?
No, 2 is stiffer just because of that bending.
Look. Don't confuse load effects with stiffness. They have nothing to do with each other. Stiffness is an inherent property of a structure. So I'm again asked the question, this deck versus this deck, which has more stiffness? Stiffness is not provided by the deck. Deck itself is very slender. As I told you, in cable stayed bridges, stiffness is provided only by the cables. So I'm asking, which deck is more stiffened, this one or this one? First one. So should we have stiff deck or should we have very flexible deck? Stiff deck. So which is better option? Now slowly you're changing your opinion. So which is the better arrangement?
First one.
First one. But why don't you see too many of the examples of them? Do you see any examples of? There are a few examples. I'm not saying there are none of this type. There are a few examples. See, we bridge engineers have been very clever. We experiment. We logically found that this arrangement gives you a stiffer arrangement. Some of the earliest bridges, not all of them, were of this type. But they found it very inconvenient to detail. As you pointed out, the crossing arrangement is not easy. These cables tend to clash with each other. You have to adjust the geometry tightly, and when you tension it, they tend to cut against each other. All that creates a problem. So we don't do too many. We go to this example. Okay, so option wise, structurally, this is better. Construction wise, this is better. And so most of the bridges, cable stayed bridges, have veered towards the second option. Okay. Now, this bridge, is it a cable stayed bridge? It's a real bridge, it's not an artist's imagination. Is it a cable stayed bridge? It is. I could say it is an arch bridge. Actually, so it's a cable stayed. Why isn't it a suspension bridge? After all, the deck is suspended from these. that is, I have a feeling, angle of the image. But if somebody took a picture from this side, you'll possibly find that almost all the cables from side view look vertical. The angle of the picture is such that it makes one think that they are. See, if you see this example, they are nearly vertical. It's just that angle. It's not the verticality of the cable. But you're right in saying that this is a cable stayed bridge. The only thing is the pylon is not vertical. And why is it not a suspension bridge? So,
Suspension cables are not there.
in suspension bridge, the main load carrying member is in tension. Here, the main load carrying member is in compression. That's exactly similar to this. The main vertical load carrying member, the difference between this and that cable straight is the pylon is vertical, and in this, the pylon is an arch. Both of them carry compression. After this load is lifted from here and transferred, they're in direct axial compression on a pylon. And in this case, the compression flows through the arch. That's all the difference is. But nevertheless, this is a cable stayed bridge, a type of a cable stayed bridge, or a combination of cable stayed come arch. Okay? Because we'll come back to some other time when we talk something about examples of arch bridges. You'll see many of them arch have got this vertical tension members in pre-stressing cables. Network arch bridges is one good example of it. Now this is suspension bridge. In suspension bridge, the main load carrying member is this cable. This is in pure tension, from which these decks are all suspended. This bridge deck is hanging from this cable. Now, what do you think is a range in which the suspension bridges the pylon to pylon distances? It can go up to 2 kilometers. In fact, it has gone up to 2 kilometers. Any idea what's the longest bridge being planned? Any idea? Okay. They are planning to push the longest span in the world to 3 kilometers, pylon to pylon distance to 3 kilometers. But for your information, I've been hearing about that bridge from 1990s. 1990s onwards, I've been hearing about the bridge. We are now almost 30 years. The bridge hasn't seen the light of the day. The reason being that when you have such a large span, you have a lot of engineering problems to solve before you're confident that you can start the construction and finish it and not leave it halfway through. So a lot of dynamic studies, a lot of wind studies, all that is being done. A lot of material studies, a lot of behavioral studies, structural behavioral studies are being done before it will get done. So typically this is all in the range of minimum 1,000 kilometers, but the older one you might see a few examples of 800 meters. 1,000 kilometers to 2,000 is generally the range. That is where the cables stay leave off. This starts. And today, if we see few more years, maybe they will make the 3,000 kilometers one. An example of a thing. And the question is, can we do a cable stayed bridge without these end anchors? Can we do, as we can say, this member is in tension. So this tension has to go somewhere. Remember, your arch had a compression and it had to go into the soil. Is it possible to avoid this anchor altogether? Is it possible? Yes, no, maybe. Who is that? I know. So I'm asking, you're repeating my question. I'm asking, this tension end anchors has been talked about. Can we design a suspension cable without these end anchors? Yes, no, maybe.
No. No.
No. But if I were to tell you that there's a bridge already built in India without this, no, sorry, I'm sorry, it's not a suspension bridge. It's a cable stayed bridge. But if you imagine that this is getting tied up here to the deck, this is getting tied up to the deck, then can this member not take the axle like a tied arch? Can you create a suspension bridge with a tying force through the deck? Possible? Not possible. Possible? Not possible. Nobody wants to answer because it will be followed with an answer why. Question why. So when you answer, please get ready with the why part of it also. Whatever be your answer. Possible? This cable to be tied to the deck and then deck acts as the load transfer member balancing out the force this way and that way. Possible? Not possible.
Sir, it's like a cantilever then.
So?
If the main span, is, if the cantilever span is half the main span,
okay,
maybe with the action of any counterweights, it will be possible, I guess.
It will be possible. So Udarni believes it's possible. Others? Deck is supported by the cables. Yeah. How did you accept the arch? Deck is supported by the arch, and the deck is also supported by the tie, and the tie was able to take the force. Tied arch you are able to accept. Possible, not possible. There are only two choices. Yes, no. Bhavdarni say possible under certain circumstances. You are asking a different question. I only ask possible. You can always say no, it's not possible. Or you can say yes, it is possible. So what do you think? Take a poll. Take a poll. Sukalyan, possible, not possible? Why? Remember, I asked you. Maybe you're afraid of the why for that follows. So you don't want to, you want to sit on the fence. So you're taken then I'll have to call out one by one. Possible, not possible? You said no. Why? Yes, it is hanging from the cable. The deck is hanging from the cable. No problem, no doubt about it. That end tension to the deck back. Only we are talking about the end tension. Like the way do in the arch. Arch also you have an end compression. The horizontal component we are transferring here. Is it possible? Therefore, in the in this. So Bhadarni said under circumstances. Sukalyan said no. Shreya?
So maybe.
Good fence sitting. When is it possible? Then in next question for you, the question will be when is it possible, when it is not possible, if it is maybe. So when it is obviously maybe means possible and not possible. So when is possible?
Sir, if the force in the cable can be the components of the force can be properly supported
So what do you mean by that?
in
We
the
want, as I
deck
told
slab.
you, correct expression.
In the deck slab.
Anchored into the deck.
Yes.
Okay, right. Okay. Akhtar, so then that under those circumstances, if the detailing is correct, you feel it's possible. Akhtar?
Yes, sir.
Possible. Possible, not possible.
Possible, sir.
Okay. Shojit, I have to do quick. Shojit? I think it's logged and gone out. Vishal? Possible, not possible. Vishal? I can't hear you.
Hello?
Now it's okay. Tell me, is it possible or not possible?
Not possible.
Not possible. I'll come back to you as to why. Then, Sutimol.
Not possible, sir.
Okay, we'll all come back to the not possible guys with why. Saurabh?
Yes, sir. Like in some circumstances like that.
Okay. So you're also that kind. Sometimes it is possible, maybe some detailing. Milind?
Yes.
Sir, not possible, sir.
Why? Now I'll ask those people who said not possible, why? Any one of you can answer quickly.
सर आर्च ब्रिज में जो बेंडिंग मोमेंट होता है वो
There is no bending moment typically in arch bridge if the geometry is right. In a suspension cable, on the cable there is only axial tension. When it comes to an anchor, because of its inclination, it has got a vertical and horizontal component. Okay, we are talking about the horizontal component. Can I transfer it and anchor it into the deck so that I don't need a strong ground anchor for taking such large horizontal forces?
तो सर वो सर मैं इसलिए नहीं बोल रहा हूँ क्योंकि जब वो केबल डेक स्लैब पे आएगा तो उसका हॉरिजॉन्टल जो फोर्स आएगा दोनों तरफ से वो तो बैलेंस हो जाएगा पर वर्टिकल जो फोर्स
ओके वर्टिकल के लिए एक फाउंडेशन है वर्टिकल के लिए एक फाउंडेशन आई कैन प्रोवाइड फॉर अ टाइम बट आई एम टेलिंग इवन ओके फॉर दोस हु have said maybe, I'll tell you, let us say you anchor it properly. Shreya said if you possible to anchor, Bhadarni said if you anchor it, you have transmitted the axial compression to the deck. Okay. Between pylon, it's a compression member. What is the length between pylon? A kilometer. Correct? Can you make it structurally so stiff that it will not buckle? What do you think for a kilometer long axially compressed member's buckling strength will be? Even if we transfer it, it's addressed to Shreya also. If you say I tie it, anchor it, and I transfer the axial compression onto the deck. What do you think will be the buckling strength of a kilometer long, or even if it's say including end to end, that there's nothing at the pylon, so it's about 2 kilometers long axially compressed member. And let's say I provide only bracings connection at the pylon to lateral restraint. So it's 1 kilometer long axially compressed member. Can you ever make it? It will be ultra slender, right? Not
Yes,
just slender, it will be ultra slender. So practically it is not possible to engineer it and therefore you don't attempt it. So you always put it onto ground, whether it is the store belt, whether it is the Tigmau bridge or whether it is the Golden Bridge, all of them are anchored into the ground very firmly and strongly. And if you have Are you, any one of you James Bond movie fans? An old James Bond movie had a very beautiful fighting sequence picturized on the cable of the Golden Gate Bridge. And the Golden Gate Bridge's cable diameter. Just remember, Golden Gate Bridge was built in 1930. Almost 100 years old it's going to be. 1930. And in India, we don't even have one. Golden Gate Bridge in San Francisco Bay Area was built in 1930. The diameter of the one main cable it's only 3.5 feet. This big. And it is not made of a single piece, it's made of many wires. There's a huge technology to do. Okay, fine. So that is a pure tension member. We'll come back to the complications related to pure tension member and the way they behave under and how the stiffness properties vary as we study further. Okay, so we have gone through the whole gamut of superstructure from a bending plus torsion to axial and tension to axial tension and axial compression. Then we are going to pure axial. Then we are going to deck significantly taking with pure tension. Of course, in the deck member there is some bending, but they're much smaller than that with the spacing of the suspender. So we practically call it a non-bending element and the stiffness that we provide for it. Okay, so now that's how we have seen a whole spectrum. So you have to have in mind what kind of a load transfer mechanism is taking place in what kind of a superstructure arrangement. So we have now moving on from one component of a bridge system called superstructure to the next component is bearings. Bearings are between the superstructure and the substructure. So let's start with a simple arrangement. We talk about a simply supported span, and from analysis we will be able to get the fact that the axial line of the bearing, when it comes to initially if it was horizontal, under the action of this load will undergo rotation alpha with respect to the axis coming out of the plane of the screen. So that is how the rotation is accommodated, and this rotation is accommodated in a bearing in the end, which is traditionally we call it as a rocker bearing because it rocks this way, allowing for the rotation, and we had a roller which also rocks as well as allows for a movement. This is the classical arrangement for rocker cum roller. This allows for rotation at one end but does not allow for horizontal displacement, and this allows for rotation as well as displacement. This we get it from the analysis, we can get the magnitude of this. This is how the rotation comes about in any bridge deck which is undergoing transverse loading. Any bridge deck, doesn't matter whether it is slab, whether it's box, whether it is truss, whether it is cable straight, every one of them will have, and they will need to have some arrangement, have different articulation. So these bearings are sometimes the word used for them is articulation. So this is traditionally a rocker and a roller type. Now if you zoom in into this area, you will notice that when you find the arrangement, the rear end moves backward, the top end, the bottom end of the slab or a beam moves backward, and the top end moves with respect to this, and the vice versa happens here. So there is a small displacement this way also. So you need to accommodate that in the what they call it expansion joints that you provide at this location, because this point is where is the road surface, and at this place this was originally when it was having no live road, it was vertical, and when you have a rotation it moves this way and this moves backwards. Okay, or on the other hand, if this doesn't move, this line will have to be shifted here. The CG line of the load will acting point will shift, and there will be a small moment also can come in due to the eccentricity. But there will be a lateral displacement in this direction, and that much can happen in that direction. This is also consequence of a rotation. So this kind of a rocker arrangement was made classically in the olden days. Of course, now with all that we understood few primary check which must be done with every bearings. All bearings cannot be rocker in all directions. A single bearing cannot be a rocker in all directions. And one thing is main reason is it's not possible to manufacture such bearing. That means it allows what they call it a rotation in all the three directions, it is not possible. Neither can all rollers. When it was classical, please remember this is not to do with the modern bearings. In classical roller bearings, rollers could not be manufactured like ball bearings, which allow movement in all directions. They were only possible to make in tubular sections, and therefore they could roll only in one direction. So rotation was also about one axis. Rigid body motions were also allowed in one back. This is how the oldest railway bridges you will see an example of rocker and roller. This is how you could not do rocker in both directions. Okay, it was not possible. They tried in few places. It was very difficult to manufacture, so they gave it up on it. So typically, this is the kinds of movement that we are talking about. So it is not possible to make rockers in all direction because of the manufacturing, and you cannot have rollers in all direction. So a more modern understanding is based on the freedom of movement. So what we did it, we translated into one of the three types. We called it as a free, guided, or restrained. This is the restraint. Whenever you see a symbol like this, that means there's a bearing which does not allow movement in any direction. It does not allow movement. When you see a bearing with this kind of a sign, it says it allows movement in the x direction. When you see a bearing of this type, so this is called a restrained bearing. This is called a guided bearing. And when this is there, that means it can allow movement in both directions. Then it is called a free bearing. So nowadays, the bearings are understood in any one of these three or a combination of all of this. So to recap, this is a restrained bearing, this is a guided bearing, and this is a free bearing. And in all these bearings, rotation is allowed in all of them in both about the y-axis as well as about the uh, x-axis. Both the rotations are allowed this way as well as that way in all these bearings. So unlike the rocker, this is how the modern bearings are constructed, not the old rocker and reversal. I don't know whether I have a photograph of a rocker and bearing. I'll locate it and show you possibly before the next class if I can look at how a traditional rocker and roller bearing looked like. Okay, or maybe we'll come back to that later on when we are in details of this bearing. We will see that. I have some. Okay, so on a simply supported span, a typical bridge axis, if you say it's an x and y, x is the traffic direction and y is transverse direction to so to say. So as we said, this is the fixed bearing. This is a guided bearing in which the guiding allows movement in the transverse direction or the perpendicular to traffic. This is also a guided bearing, but this allows movement in the longitudinal direction or the traffic direction, and this is a free bearing. Now, this is the kind of a bearing arrangement which is seen in this. Okay, so now when you look at it, this left one, if you take a bearings in pair, let us call this as the left side. So in the traffic direction, what happened? This bearing does not allow movement in this direction. This bearing also does not allow movement in that direction, whereas this bearing allows movement in this direction and this bearing allows movement in this direction. And when you look at this bearings in pair, this bearing does not allow movement in that direction. This also does not allow movement in that direction, but this bearing allows movement in this direction and this direction. So then if such a bridge deck, if there is an expansion, what can cause expansion? Say a temperature rise takes place. And what happens is that the bridge is free to expand and it will expand in this fashion. It will expand in this fashion. In this direction also it can expand and in that direction also it can expand. And if you, what do you call it? If there is a contraction, then it will contract this way. I have contracted it so much that it looks as if it has come off the bearing. This is only to visualize it. So that means bidirectional contraction also is to be accommodated. So when you have this type of bearing, and if this is the permissible motion, do you think temperature will cause any stresses on this bridge deck, or rise and fall of temperature or expansion and contraction? Will it cause any stress on the bridge deck? Yes. On that bridge deck, will it cause any stresses? That type of a bearing arrangement.
No, but friction offers some resistance.
What is that?
Friction offers some
I'm
resistance.
not able to hear you clearly.
Hello, sir.
Yeah.
Friction offers some resistance. Other than
Fine.
that, no.
Okay. So we can call it either friction or you can call it bearing stiffness. Okay. Barring that, will there be any other? Let's say this was ideal. No friction. No friction. Then will there be any stresses in the deck? No, we are not talking about that yet. We are just talking as if for let's say it is a slab type of bridge, a thin slab type of bridge. I think let's not complicate that. We look one at a time. Let's look at the problem in a planar sense. If we have this type of bearing arrangement, will there be stresses in the deck due to expansion and contraction? Please remember when we talk about variation in temperature from top of deck to bottom deck, we don't use expansion and contraction. We use the word temperature gradient. You're familiar with the term?
Yes, sir.
So we don't use
Yes, sir.
expansion and contraction for that. For that, we use temperature gradient. So I never use the word temperature gradient. For expansion and contraction, will there be stresses?
No, sir.
No. Okay. Do everybody agree? Or you are again disagreement and you want to sit on the fence? Okay. So you say there will be no stresses, right? Now, if we had the same thing in skew, and if we made this arrangement, do you think there will be any stresses in the deck? Now fence sitting will start. Yes? Will there be stresses in that skew deck?
Yes, sir.
There will be stresses. Why?
The line of guidance, that articulation.
Mhm. Okay.
If the line of expansion is not matched with that guided line of the bearing, it will cause some stress.
Why it will not? See, the idea behind expansion and contraction is this length will reduce. This
Yes,
width will reduce.
Yes.
And if it reduces in that direction, you will always have this permitting movement and that permitting movement. And this anyway permits movement in all directions. So that means it will be when there's a reduction, the reduced cross section will be like that. When it is expanded, the expanded cross section will be like that. So will there be any stresses in this arrangement?
But the long direction restraint in the free bearing is like somewhat skewed in other direction.
No. See, that is, what does that mean?
That is
When that double arrow literally means it's free in all direction. Free bearing means there is no restriction. It is not as if it's guided on those two directions only. No, I think you have misunderstood that symbol. That symbol means it's free in all directions. So will there be stresses due to that? This arrangement in a skew bridge deck. Yes, Shukalyan? No. Okay. At least we have others want to keep silent, but somewhere along the line we'll have to make them all talk. Okay. So now let us say we have, instead of a simply supported single span, when you have a continuous span, so there is a bridge deck which is curved and it has 1, 2, 3, 4, 5 supports. Okay, out of which one is the fixed bearing. This is free, and these are all free, all on the outer end, and these are the guided bearings. This kind of arrangement is called polar radiating bearing arrangement for continuous structures. What is it called? It's called polar radiating bearing arrangement. Right. As opposed to that, you have an alternative arrangement which is called the tangent bearing system. The bearing distance arranged tangentially. That means you have a fixed bearing, you have a transversely guided bearing, fully free in all the others, and then you have the guided bearing which will go tangent to the radius at the support point. Right? So the question is, this is very commonly used bearing arrangement. It is not uncommon. Now question to you is, in this bearing and in this bearing, which one will have stresses due to thermal expansion and contraction? First one, second one, neither, both. First one is this, that is, I'm talking about this arrangement and this arrangement. Things are becoming interesting. Now there is a silence. Will there be stresses due to expansion and contraction? If so, for which arrangement? If not, for which arrangement? Or if not, for both? If yes, for both, which one? The choice, a fourth choice. First arrangement, second arrangement, both arrangement, none of the arrangement. Will there be stresses?
Second arrangement.
Second
Having
arrangement
stress, more stress.
will have stresses.
Yeah.
Okay, so one choice. First one will not have.
I think first one will not have.
Okay. What about others? Why others are not answering? Take a call. After all, we are among friends. Both. With Shukalyan. Okay. Shukalyan says both will not have any stresses. Right. Then others? Or should I take a call, poll again? Shreya, Akhtar, one by one. Milind. Saurabh, I know today Sujit cannot speak. He is a Maunvrat today. His mic has given up on him. He can send a message. Vishal. Shruti Mol, what is your idea? Oh, today other one is, she's Naina is not joined.
Both case, there will not be any stress.
Okay. So take a call. Yes. No stress is Shruti Mol. In line with Sukalyan. And Bhavadharani says second one will have stress, first one will. Still want to stick with that? First one will have or no, will not have?
First one will not have.
Okay, first one will not have, second one will have. Okay, what about others? Saurabh, Milind, Vishal, Shreya? Why nobody is opening them up? Yes, Shreya.
The second one will have some stresses.
Okay, first one?
First one will not have any.
First one will not have. Okay, what about Akhtar? Akhtar? I think next time I have to insist everybody keep the camera on. Vishal?
The first one will be having stresses and second one I think will not have.
Okay, so you're going the other way around. First one will be stress-free, second one will be with, sorry, first one will be with stress, second one will be stress-free. Okay, that means
Yes.
you're saying the polar one will have stresses and the tangential will not have stresses. Okay, then what about Saurabh?
Sir, in both there will be no stresses.
In both there will be no stresses. Now I have got a call for everybody. Milind?
पोलर में नहीं होना चाहिए और टेंजेंट में होना
इसमें
चाहिए।
पोलर में नहीं होना,
हाँ,
एंड टैंजेंशियल में
जैसे दिख रहा है उस हिसाब से होना चाहिए उसमें स्ट्रेस।
ना ना,
और कंफ्यूजन है इसमें, मैं क्लियर नहीं है मेरा, मैं तुक्का लगा रहा हूँ, सीधा बता रहा हूँ, मेरा क्लियर नहीं है।
Right, okay, so it's a guess. As what Milind is trying to explain is he is guessing that the polar one will not have. That's what you said, right?
यस,
And
पोलर
the,
में नहीं होगा और इसमें होगा,
right,
क्योंकि इसका
okay. If I were to tell you under circumstances, all of you are correct. Under circumstances, all of you are wrong. Now comes the question, what are these circumstances? Okay. Now, as long as you have expansion, contraction, or change in dimension due to volumetric effect. What are volumetric effects? Temperature is volumetric effect. Shrinkage is a volumetric effect, correct? As long as you have a volumetric effect for polar radiating arrangement, you will have no stresses. And for tangential, you will have stresses. You will have restraints to free movement. But there's yet another, if on the other hand, if your bridge deck was pre-stressed concrete, in the case of pre-stressed concrete, there is another phenomena which causes deformation, which is creep. Creep is not a volumetric dimension change. Creep is a linear dimension change. That means it follows the axis of the member. Once it follows the axis of the member, then tangential will not cause stresses, polar will cause stresses. Right? So now comes the question, when should I use what? If you have doing a continuous structure which is RCC, go for polar radiating because it will only have volumetric changes. If you are going for pre-stress, then go for polar radiating if temperature and shrinkage contribute to a larger deformation than creep. Go for tangential if creep causes the larger deformation. Which means what? You will have to do a preliminary estimate and then take a call. Construction wise, what is easy? If I were to send you to the site and you have got say 4 into 30 meter, 120 meter continuously curved deck, and I were ask you to install the bearings, which you would find easy? Polar or tangential? Easy to install.
इजी टेंजेंशियल होगा।
Tangential, yes. That is why it is very common. Okay. When do you need to worry about it? You need to worry about it if you are planning continuous structure on very tight radiuses. If your radiuses are generous, what I mean to say, if the radius is of the order of 120, 130, 140 meters, they are tight, reasonably tight, but not that tight. For bearing purposes, they are not that tight. And in that, if you have spans in the range of 25, 30, 35 meter span, tangential is okay. Because as engineers, what is our job? We don't have to give the one in which the forces are the least. We have to give the one where forces are less, not necessarily these, but construction is easy also. if you give an arrangement where construction is very difficult and due to construction your aim is not met, there is no point in making this suggestion. So therefore, somewhere along the line, you have to balance out all this and take your decision. That is why if you notice the slide, you have noticed that the tangential one has commonly used criteria because it comes from our normal application on the bridges. All right. So now when you look at this, then you go back to the simply supported. Now you tell me this. This is what? Polar radial, correct? This is looking at the fixed end. This is looking at the fixed end. So it's the radial polar. This is free anyway, it doesn't matter. So this will cause no stress. So whoever they chose for thermal ones that it will cause stresses for this Q, not correct. If you say this, no stress for thermal, this stress for thermal, but no stress for creep. Right? Now coming back to two-span continuous structure, we have a choice. We have this polar radial arrangement. That is, this is a fixed pier. So this guiding is toward the fixed one. This guiding is toward the fixed one. This guiding is, that is why it is called radial. Is to understand, maybe the terminology was not clear. All the guide bearings are looking towards the restrained bearing. All of them are oriented towards the restrained bearing. Then it is stress free for thermal expansion or volumetric change based forces. So by that logic, both this is also polar radiating, and even if it is Q, it is polar radiating. It will cause no stresses in the thermal one. The question now is, you have choice. You have a choice to put the restraint bearing on this or the restraint bearing on this. Which is better?
P arrangement is better.
P arrangement is better. Why so?
It is in the zero moment point.
In a way, yes. That is one advantage in the P. The extent of movement in, just let me get my pointer out. This, if it is the so-called restraint pier, the movement here and the movement here will be smaller. In this case, the movement will accumulate to this. Okay. But under what circumstances will you avoid doing or go for this? There is, from movement point of view, you said P choice is correct. I agree with that. But there are certain circumstances wherein the Q choice might be better. As engineers, we must be aware of both this. Both of them are polar radiating. Please remember that here also the guide is towards this fixed one, all these guide, and free doesn't matter. So under what circumstances will you choose Q? Or the choice of this arrangement, P arrangement versus Q arrangement, will depend on what all factors? Or the other way around, Bhavtarni, you will choose P always? You are the one who chose P, na, first.
Yes, sir.
So will you choose this P always?
No.
Huh?
Have a confusion, sir.
So that's exactly the point. We must challenge all our preconceived notion, then we'll have a better learning for it. So I'm asking a question, if you're going to abandon P sometime you may abandon P, under what circumstances will we abandon P and go to Q? That's interesting. Not the fact that we always do P, we also do Q. But the question is, under what circumstances will you switch from P to Q? I don't want to exit this because the answer then will get revealed. So time now.
I think
35.
due to creep effects. No. Okay.
Okay.
Sir,
Yes.
सर इसमें स्पैन कंटिन्यूटी के ऊपर तो बेस नहीं है ना ये कहीं कि
It is a two span continuous. For two span continuous, you have a choice like this and a choice like this. The question was, which is preferable? Bhavdarni chose this, stating that it minimizes the size of the expansion joint at the two ends of the continuous unit. I ask next question, under what circumstances would you prefer to go for Q? Is there any circumstances at all? Or no, it should always be P? That was the question. So Milind, you tell me now, what do you believe? Should it always be P? If it is not, under what circumstances will you choose Q?
सर वो यदि स्ट्रेट मेरे को ऐसा लग रहा है कि स्ट्रेट जाएगा तो हम पी वाला अरेंजमेंट लेंगे और यदि आर्क होगा तो
No. Both of them are straight only. We will not change. We will not put too many variables. We handle one variable at a time. You remember in the maths when you do constraint problem, you don't take 10 variables and then get puzzled and bog down. This variable has this result, that variable. One variable, straight bridge. But two span continuous. Now you're adding another variable.
तो फिर क्यों ज्यादा सही लग रहा है?
हाँ?
क्यों ज्यादा सही है मेरे?
क्यों?
जी क्यों इसलिए ज्यादा, मतलब मैं क्यों को क्यों इसलिए बता देता हूँ कि मेरे को ये क्यों लग रहा है, क्योंकि ये कंटिन्यूअस स्पान है तो जब एक्सपांशन होगा तो दोनों का एक साथ होगा. और
what Bhavdarni explained was, if this is the restrained foundation, the movement at this joint will be proportional to this length. If this is the fixed one, the movement at this will be proportional to this length. So the movement will be doubled if the spans are equal. Or it will be equal to the total length of the bridge as far as the movement is concerned, whereas here it will be equal to the contributory length. The side of the side, if they're equal, then they'll be equivalent half of what you will. That's the reason she chose P. Now you are telling Q. So I ask Q, it cannot be the movement, because movement you are only magnifying. Under what circumstances? So, or do all of you now agree with Bhavdarni and say we'll never choose Q?
No, sir, depends on the substructure design also.
Okay, so that's one variable you have got. Okay, now because I'm running out of time, we don't use the word substructure. As I said, we want to use correct choice. Flexible soil or flexible substructure in the intermediate pier. If the intermediate pier, see if this is the restrained one, all the longitudinal lateral load for wind, earthquake will all go to this. So if on the other hand, this soil is weak compared to the so-called side soil, then you would want to shift it here. However, if these spans are very large, then the accumulated movement is large. That's a valid point in that also. But if these spans are smaller, in the sense that your expansion joint, the simplest of the expansion joint can handle the combined movement, then it may be possible to do this. Under a combination of flexible soil under intermediate pier and smaller span length, Q might be also possible or might be preferable, especially if the flexible soil or the foundation, the whole substructure system is much more flexible than in the normal. Then in that case, you can go for Q. Though it accumulates, in which case you have to ensure that the expansion joint doesn't become complicated. Okay, so as engineers, we have certain circumstances. We should know full background of the bridge before we take a call. Just don't take a call on the basis of one information. Ask. Okay. Now coming back to two span continuous bridges, you should never have bearings of different stiffnesses and different thicknesses on the same pier. If you are using this type, when you have a lateral stiffnesses, loads will be redistributed from more flexible to stiffer bearing if you did that. So whenever you are choosing bearings on the same pier, that means these two bearings are on one pier, these two bearings are on one pier, they should preferably have similar stiffnesses, both vertical as well as horizontal, as far as is possible. Okay, so that's what you should do. Otherwise, you will have vertical load. If this and this had a different vertical stiffnesses, then what will happen is there'll be something equivalent to support sinking problem. Your reactions will not be as you anticipated equal distribution. They will all more flexible will have less load, more rigid will have more load. That kind of a situation will arise. So you should never do bearings of different stiffness or different materials on the same pier. That's another rule about the fundamental rule about the bearing. All right. Now, what is the what do you call it? Movements at the bearing. We have the freedom. Basically the accounted movement. So we have freedom to move under external and temperature changes. So if you have a hot and cold, they will cause hogging. So you should have that kind of a rotational capacity. And if you have fixed against translation, you should have that free to slide in one direction only, fully free to slide horizontally. These are all the movements at the bearing that you must accommodate and design for. All right. Now, if we take a look at some such arrangement, we have a span and we have two bearings close to each other. Is it a good arrangement? You should avoid this because of the uplift on this bearing, because no bearing should have uplift and pounding. Because once this load is here, this will lift off. When this load moves and comes here, this will go and bang against the bearing. This kind of pounding should be avoided, and therefore, wherever lifting of deck from support is possible, you should avoid such bearings. It is better, if possible, to increase the span and go for a single support and single bearing rather than say I will reduce the span by doing this and this kind of gimmicks. Okay. And bearings generally are incapable of resisting uplift. There are certain ways of detailing tension bearing. There are certain ways, but they are complicated and unnecessary complication. It is better avoided. So you always should avoid uplift on this bearing. This is another thing that you should, in these kind of special cases where somebody gives you an idea that I have two bearings close to each other on a continuous structure, so I can reduce the load on bearing. All that is nonsense. Avoid doing that. Okay. Then you have the issue, you have problems with straight bearings, single span, skew spans, and multiple span. You have single span, skew deck. All these you have to be worried about in terms of how you arrange the bearing. So think, always remember in terms of polar radiating versus tangential. So keep that in mind. So you have all these various possibilities. Some of them, right? In the non-straight bridges, how does the movement of the bearing take place? Again, depending upon the nature of the movement, if it is volumetric, it will go in certain fashion, and if it is linear like creep, it will go in a different fashion. So you need to make sure that you have the right kind of arrangement depending on which is causing the major. For example, if this movement is more or less straight like that, then you could also provide tangential here without any problem. But if on the other hand you have a curved deck which is going this way, then you need to provide the one which is radial for thermal movement. So all these are issues which is related to the breathability of the deck. Okay. Then you have an issue in special cases when you have skew decks and you have a slab type of bridge. When you have this, there's the possibility of the lift off at all the acute corners. Do you recall why we provide the top steel at the acute corner? If you recall your old IS 456 expressions, you need to provide for a negative reinforcement here. That comes out of the possible lift off, and you have to avoid it. Okay, and that then you have to avoid multiple bearings. When you should try to avoid at any one end, because if you have with overhang and live load, this will tend to suffer under both lift off. The reaction on this bearing will be an unknown, and therefore, and even in thermal expansion in the transfer, if the deck is wide enough, then you will have, for rising temperature, you will have a hogging displacement, sorry, not moment, hogging displacement in this direction. It can also undergo lift off. So this reaction will get transferred. So multiple bearing at a simply supported one are also should be avoided, especially for wide deck. Go for well-determined force transfer mechanism when you choose bearing. Okay. Right. Then these are the types of bearing, just visual pictures. And this you can see is a free bearing. The freedom is achieved by having a Teflon sheet at the top and a stainless steel plate along this, so that the friction between them is very small. So it is free to slide in both the direction. This is a very typical on rubber bearing, elastomeric bearing. The other types of bearings will come. This is the simplest of the bearings, you can see. And this is the guided bearing, wherein what you do is this Teflon and this is split into two halves. You have a guide like this so that it prevents translation in that direction but allows movement in this direction. This is what is a typical arrangement for a guided bearing. And when it comes to a fixed bearing, what you end up doing is you restrain movement this way, and by putting down stand like that, you restrain movement in that direction. So it becomes fixed in both direction, and all of them have got elastomeric bearing as a vertical load transferring member. Okay, and this is how the classical rocker and roller looks like. I was looking for photographs. You have it here. So you have this type of arrangement. It can only rotate about that axis. It cannot rotate in the perpendicular direction. So therefore, old bridges always had this kind of a problem. They couldn't allow you to breathe in two directions. Modern bridges. So, or you have the roller bearing where you have a rocking arrangement at the top and the rollers are all hidden inside this box. So this allows for translational sliding. Then modern bearings are elastomeric bearing. They are reinforced with the stainless steel plates inside this rubber. If you cut a cross section, they will look like that. They will have rubber layers interspersed with the stainless steel plates. These plates are essentially required as called reinforcement in the rubber so that it doesn't undergo significant distortion in the size under the compression load. As you understand and you apply the compression load, rubber as a material has a very high Poisson's ratio. There will be a lot of lateral deformation, and to reduce that lateral deformation, the bulging will take place. To reduce the bulging, you provide for the shear reinforcement in the plate, and these plates are in tension and the design is also in call. We'll deal with that when we come to taking some of the design rules for the elastomeric bearing. Then you have what is called as a lead rubber bearing, basically the elastomeric bearings with a lead core. This is used in isolation devices under seismic conditions so that they provide for energy absorption. We will deal with that in a greater detail when we understand the principle of hysteresis loop and the energy dissipation during the earthquake engineering, that portion of it. But keep remember in plan, this lead rubber bearings, when you hear it, it's nothing but elastomeric bearing with a core of lead underneath in between. And these are basically symbols for what you call it, restraint bearing, a guided bearing, and a free bearing in pot bearing. And the pot bearing arrangement is something like this. You have a pot in which there is an elastomeric disc. On top of the elastomeric disc, you have PTFE, just like we saw in elastomeric bearing. And the piston will sit on it. And this is actually a guide. So it will prevent displacement in this direction. It will allow movement. This is a picture of a guided pot bearing. This is how the assembled pot bearing will look like. You can't see anything basically inside, and the content is like this. There's a pot, there's an elastomeric disc, there are sealing rings, and there's the piston which sits on it. Then you have the PTFE sliding bearing. This is the guided bearing. You can see this restrains against the side plate, and this is the elastomeric bearing with pot and PTFE. This allows for the sliding, and it is also non-stick, reduces the friction. This pot PTFE sheets here. We will move to shock transmission unit next class. Today we will stop at this bearing and we will see this as other arrangements for sharing the loads. We have 10 minutes today for the question and answer session.
सर वो इलास्टोमेरिक बेरिंग को हम किस में लेंगे? उसमें वो गाइडेड की तरह है या फिक्स्ड की तरह है? क्योंकि उसमें रबड़ लगा था.
There are if you have no PTFE, that is you don't have a free sliding, but you want the shear strength. See, there are two ways to use elastomeric bearing. Elastomeric bearings are used to accommodate only the vertical load. In which case what happens? Vertical load and rotation. You cannot avoid rotation, but you don't want sliding to take place. Then what do you do? On top of the elastomeric bearing, you put a PTFE and the sliding arrangement you created. So what happens is, because PTFE and stainless steel have got very low friction, so the movement, the deformation will not get translated to the bearing, but the rotation of the deck, which will be transmitted to, that will get transmitted to elastomeric bearing. Vertical load definitely will get transmitted to elastomeric bearing. So there are two ways to use elastomeric bearing. vertical load and rotation only, or vertical load, translation and rotation. You can use it in both. If you are using in the second mode, that is you want also the translation to be accommodated in the bearing, then you don't use PTFE. You allow the concrete and the rubber to be in contact with each other through some kind of a cementitious bond, either cement bond or epoxy bond. Then when the girder moves, the rubber also deforms. We'll look at that when we come to the design of the bearing. So it depends upon what all forces you want elastomeric bearing to take, what all deformations you want the elastomeric bearing to accommodate. That's your choice. As an engineer, you have a choice. I don't like the idea of rubber bearing deforming laterally, so I will put PTFE. No, I don't mind them deforming. I will remove the PTFE. Both the options are available.
मतलब सर उसको जब भी हमको देना होगा तो हमको पीटीएफई को यूज करना पड़ेगा, मतलब वो
जरूरी नहीं है. You miss the point. If I can accommodate in my design the lateral deformation to be accommodated by the deformation of bearing, rubber itself deforming, then I don't need PTFE. But if I want to avoid the lateral deformation of the bearing, then I should put PTFE and eliminate that movement by reducing the so-called friction between rubber and concrete to friction between rubber with pasted PTFE and stainless steel. Then the deformation will take place by a free sliding on top of the PTFE, which is very small deformation will take place. Okay, but rotation anyway will be taking place on the rubber. We'll come to that when we discuss the design aspects of the rubber bearings. But remember that you have a choice. You can do both. It makes your life complicated. Where to choose what? Always go for the simplest solution. Always go for the simplest solution. That's how you start the engineering. You make it complex slowly. If your design circumstances are such, maybe very large movement, I can't design a bearing. Okay, I'll reduce the movement. If you reduce the movement, then you find that the force transfer changes. You need to provide a fixed bearing. If you share the movement, you need not provide the fixed bearing. These are all advantages and disadvantages. We will see that when we come to the details of the bearing. I'm only introducing the bridge component first, then we will go to in-depth design issues for each one of them. I hope that pace is okay. Instead of telling all about bearing, then you'll forget. So right now we're starting with superstructure as component, bearing. Next we will go to substructure, and then we will go to the foundation, then we'll go to the soil, and then we'll start with the detail of superstructure, detail of bearing, and the detail of substructure that way, so that we introduce it in packages. Instead of telling you all about the whole lot thing, you'll be too much flooded with information. Meanwhile, continue with the reading of the material that I given to you as a reference books for this. Choose your choice. Start reading a little bit every day. I don't want to take a poll to ask how many of you have read anything so far. I don't want to be disappointed.
तो सर स्पेसिफिक किस बुक में मिलेगा?
देखिए साहब, this is a material from a variety of books. Okay, this material is from a variety of sources. Why? Because I don't have the luxury of sitting with you for next 4 years to give you a conduct course on bridge. I have 30 weeks in which to tell you these are all the aspects. I want you to spend more time. So I've given you a list of books in the beginning. Nidhi would have shared it with you. You find a book. Read the book which you think convenient for you. There are about 8 or 10 books I have given in the list. Have you seen the list? The face, those who have kept the camera on. Now I understand why everybody keeps the camera off. I can read some expressions. For others, I'm blank. Maybe you've not seen the list at all.
सर उसमें जो बुक है वीके रैना जिसका सेकंड उसमें सेकंड एडिशन 1994.
Yeah, VK Rana is a little outdated book. I would prefer if you look the first one, the Chinese authors. It's a very fat book, very, very fat book. I cannot do justice to all of it. Okay.
तो क्या नाम बताया सर वो चाइनीज ऑथर का?
यार मेरे को भी वो लिस्ट खोल के दिखाना पड़ेगा है. हाँ. Yes, exactly.
ठीक. Yes.
ठीक है.
जी.
Right. Questions for the day. We have 5 minutes. Too many questions, too little time. I want, by the time we finish the course, I think we should be able to have a free conversation without constraint between at least the 11, 12 of you and myself. There should be no hang-ups. I find a lot of hang-ups among you to say, no, should I say, should I not say? I sense it. I'm not saying it is true, but I sense that after looking at it, everybody is, I'm not calling it shyness, but I would say diffidence. I want you to overcome that, at least within this group. You should have no diffidence at all. Be free. Okay. And as I told you, one of my main aim is to make sure that all of you, from silence, you all become very talkative. May not be as talkative as me, but to some extent. You're muted, Milind.
सर एक डाउट पूछना था अभी सर मैं पीएससी गड्ढा डिजाइन कर रहा था 30, 40, 35 एंड 40 मीटर.
ओके. स्टैंडर्ड डिजाइन कर रहे हो?
नहीं स्टैंडर्ड डिजाइन का भी पारी आया नहीं है. मॉर्स के कर रहे हैं काम, पर वो सीट को देखने के लिए बोले थे सचिन सर. तो मैं जो हमारा स्तूप का जो सीट था जो नॉर्मल जो डिजाइन के लिए यूज होता था, मैं सीट को वापस मेरे को बनाना पड़ा क्योंकि उसमें कुछ गलती था. तो बोले कि एक बार वापस बनाओ. और मॉर्स के लिए एक सीट ऑलरेडी बना हुआ है और डिटेल उसमें मतलब किसी पॉइंट को नहीं छोड़ा गया है. तो पर उसमें हमको थोड़ा सा वैल्यू को चेक करना था, कहीं कुछ गलती तो नहीं है, इसलिए साइड बाय साइड. तो सर मेरे को सर जो उसमें जो प्रिंसिपल समझ में आया जब अपना प्री स्ट्रेस का है, प्री स्ट्रेसिंग में सर हम उसको स्ट्रेस दे के एक हिसाब से मतलब हम उसको टेंशन पे लाते हैं. हम उसको टेंशन पे ला रहे हैं जिससे एक्सटर्नल लोड जब टेंशन लगाएगा तो वो उसको बैलेंस कर देगा, काउंटर बैलेंस करेगा. तो इसका मतलब ये होगा, मतलब मेरा ये पूछना है कि यदि हम ब्रिज के हर कंपोनेंट को यदि हम टेंशन पे रखें इंटरनली तो वो ब्रिज ज्यादा ड्यूरेबल होगा. तो इसलिए पूछ रहा हूँ कि जैसे हम क्या किए, पीएससी गर्डर को प्री स्ट्रेसिंग के टेंशन दिए, पर स्लैब को हम जब डिजाइन कर रहे हैं, स्लैब जो है मोनोलिथिकली वो ऊपर नॉर्मल डिजाइन हो रहा है आरसीसी. तो यदि मैं स्लैब को ट्रांसवर्सली भी प्री स्ट्रेसिंग कर दूं.
Okay. Then let us understand, we will understand sometime later, not now, we'll understand sometime later. How do you transition from reinforced concrete to pre-stressed concrete? You have to understand that will be, if you saw the transition from slab bridge to box girder bridges.
Yes.
What was, do you recall? That was last class. Why did we transition from slab bridge to box girder bridges?
सर उसमें हम वो क्या बोलते हैं,
primarily went because we are ambitious to do longer and longer spans. Slab bridges were small span, so small spans RCC good enough for economical. If you try to do long span RCC, it will be very uneconomical. Similarly, if you do small spans pre-stressed concrete, very uneconomical. You cannot do, let us say, especially in a simply supported spans, practically it is totally unadvisable to do pre-stressed concrete of spans less than 16, 17 meters. I don't know, how many of you have studied pre-stressed concrete formally in your MTech program? Anybody who has not studied pre-stressed concrete formally?
BTech.
No, BTech is not good enough. MTech? MTech, you didn't study pre-stressed concrete. Who didn't study pre-stressed concrete? Can you just take a quick poll? In MTech, you didn't have a pre-stressed concrete course. Now, one by one. Sukalyan says no course in pre-stressed concrete in MTech. Shreya?
No, sir, it was not covered in detail.
You mean? Okay, Akhtar? Akhtar? I won't ask Sujit. Have you, Akhtar, can you hear us?
No, sir.
No pre-stress concrete course at MTech level.
मैं दोनों same college से हूँ।
I can't hear, too much background noise.
सर
I
अख्तर भाई और मैं दोनों एक ही कॉलेज से VNIT.
VNIT. No course in MTech at pre-stress. Okay, what about Shrutimol?
I studied, sir.
Okay. What about Vishal? Vishal today hasn't opened his mouth at all. I don't know whether he's there at all. Shojit, at least send a message. Have you studied pre-stress concrete as a formal course in MTech? What about you, Bhadarni?
No, sir. It's elective. No.
It was not in our curriculum. Okay. What about
It's
Saurabh?
there, sir. Actually, it's elective
Sir,
course.
it was a, yeah, for me also it was elective. I studied, but I took that subject.
Oh. So that means in this whole batch, I see formally only Saurabh and Shrutimol have studied it formally. Okay. Your question? No, okay. Nadeem Akhtar, you're okay. You're not formally studied. What I hope it was there in the curriculum. Okay. Right. My advice to you all in that case is to catch up on pre-stress concrete also. Seriously, because why I'll tell you. The question that Milind asked, why we don't do pre-stress concrete for smaller spans? It comes from the concept of losses. What are the losses in pre-stress concrete? Elastic shortening, creep, and shrinkage, and relaxation. Relaxation and elastic shortening are not significant losses, but creep and shrinkage are significant losses. So if you apply, so if the pre-stress has to be effective, the quantum of decrease in the length compared to the initial strain that you apply must be small. Then only the pre-stress is effective for a long time. And creep and shrinkage are time-dependent phenomena. This is something, though they would have done the calculation that creep you will shrink so much, shrinkage will compress so much, and this reduction will overcome for small span the total elongation, because pre-stress also you limit it to about 75% of the strength. So there is only so much deformation, elongation you can give on a strand of 16-meter length, so that you don't exceed the 75% of the breaking load. So when you put all these combination for smaller span, the effective pre-stress left after long term is very negligible. Therefore, pre-stress concrete is not used for smaller spans. So when you talk about transverse deck, your typical deck will be what? 11 meters. Well, widest deck may be 20 meters. So it is practically not economical to do pre-stress concrete. It will be not effective. So we tend to do transverse is RCC, longitudinal is pre-stress, especially the longer span. Because longer span are uneconomical in RCC. Now I am in a little bit of trouble. I assumed that all of you would have done, because look, primarily because the colleges I have come from, pre-stress concrete was a elective, but encouraged for everybody to take as a core subject. It is elective in IIT Madras also, but it was encouraged that everybody take. And if you have friends who are doing masters, who are juniors who are doing masters, I would request, if they intend to work in infrastructure field, if they intend to work in buildings, no problem, you can avoid pre-stress concrete. But if they intend to work in infrastructure field, advise them to study pre-stress concrete. They're your friends, they're juniors. Think about their future. Let them become a little better prepared than all of you, or you have cut off all your relationship with your colleges. Please advise them. Definitely take pre-stress concrete as a mandatory subject. Even if it's elective, choose it. You will have great difficulty. You will have great difficulty in understanding the nuances of bridge engineering if you do not have a thorough background in pre-stress. If that is the case, I should have added one more textbook on pre-stress concrete design itself. I didn't. I assumed that you all had a background in pre. Sorry, my mistake. Surprised that all of you are finding comfort level in doing pre-stress concrete. That means what I will feel you all end up doing is following on the footstep of what others are doing without understanding why they have done that. Now I thought, okay, in that case, then I'll have to build up some background on the pre-stress concrete. Okay. Okay, we'll do that. We'll do that. We have a long time. We have 6 months with each other, right? By the time I finish my first, second or third, fourth lesson, I want all of you to be more vocal about your thoughts. When I ask a question, right or wrong, you should start learning to exercise your judgment. Okay. Silence doesn't help anybody, neither you nor me, because I have to keep coming out, ask you questions that take some more time. And we have limited time. We have to finish the introduction within 30-35 lessons. Maybe I'll expand it to 40. So 52 weeks means 1 full year. That's a lot of time to spend. 52 into 200 hours. I don't think any course will be should take that long. Okay. Anything else? So pre-stressed concrete is a shortcoming. All right, I'll keep that in mind. Okay. Any other questions for the day before we wind up? Okay. So we meet again next Friday, same time.
Yes.
Okay, 4 to 6. Right. All right then. Yes, Sukanya. Yes. Yeah. No. 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 What it's that load that applied only to the anchoring devices, not for the or the components of the pot bearing, but not for your substructure. See, so there's a difference. Only for the components of the bearing, that condition was that you have to design it for a minimum 10%. Why did they give that? Think about it. Because it was kind of people were misusing that clause. There were people who were checking the design who says, okay, if my bearing connections are designed for 10%, you must also design the substructure for 10%. Even if it is a sliding bearing. Pot and PTFE have a maximum friction of 5%. Correct? If I am having only 5% friction, and remember one thing, I am not factually correct when I say what PTFE material is a strange material. The material has high friction at low contact stresses and low friction at high contact stresses. What does it mean? Let us say if I have a 1000 ton to transfer, if my contact pressure is 20 MPa, I will have a higher friction for the same 1000 tons. But if my contact pressure, I reduce the amount of PTFE size and make the contact pressure 40 MPa, which is also acceptable for PTFE. That PTFE smaller, contact stresses are 40 MPa. Then the friction reduces. So the upper limit of all, that is why pot and PTFE bearings are designed to be close to 2.5% actual friction range for the normal working life of it. But design forces wise, you are asked to design the whole of the substructure, superstructure, etc. for 5% friction for pot and PTFE bearing. But connection and the housing and the body of the bearing, the components of the bearing have to be designed minimum for 10%. You may transport on pin bearing, or rather I should say on the pot bearing, not pot cum PTFE. In pot bearings, you will be transferring much higher forces than 10%. You can even transfer 20, 25, 50% also. In which case you will design the structural arrangement differently. But this was meant, this 10% was meant for the free, so-called free bearing. Free in both directions, where the friction was only 2.5%, but all the body, the pot, the anchors, they all had to be designed for 10%. Then this was misused by or misinterpreted by many of the proof checkers whose sole aim was, I have to increase the quantity of an EPC contractor. So I asked them to design everything for 10%. So they removed that clause. Okay, I have designed what you call it pot and PTFE bearing, free bearings in Malaysia with no anchors. In our country, we don't accept designs without anchors. Because 5%, just imagine the sliding friction between PTFE and stainless reduces the friction limitation to 5%. The stainless steel plate and its backing plate is connected to concrete through, let us say, only a grout medium. Okay. So the friction between stainless steel and grout is of the order of minimum 30% and a maximum of 60% of the vertical load. So the factor of safety against free sliding is 60 by 5 to 12. 12 should be enough. But our code was very conservative. They said, no, 12 is not enough. You still have to provide anchors. And how that anchor is provided? Because there's a thought that in the dynamic condition, this friction bond between grout and concrete is likely to break. That's a philosophy, right? So therefore, there are conservativeness built into it, but that conservativeness was being misinterpreted. So they said, forget about it, remove it altogether. Such limitation. Design for the frictional for that itself. Anyway, we are having already 12 as a factor of safety without any anchorage system. So if you design for 5%, it is on that 12 you have an additional anchor system which is for 5% of the force. So they removed it. It was becoming over conservative. Okay. Right then. So if no more questions for the day, we'll call it a day and meet again next Friday, 4 o'clock. Okay.
Oops.
Thank you.
Thank you, sir.
Good night.
Good night, sir.
Okay.